In this lecture, we are going to discuss the calculation of interfacial tension. In the previous lecture, we have discussed about the spreading and wetting. So, wetting is a general phenomena which was describing that the displacement of air by liquid from solid or liquid surfaces. Spreading is one of the wetting phenomena in which the liquid is displacing all the surface of the solid or liquid. It means that liquid has been completely spread over this surface or the substrate. Whereas wetting can be either spreading or here we can see that it can be like a droplet or formation of lens. It's for solid surface, and if we have a liquid surface, for the liquid surface we can have lens formation like this. So here we have a liquid and this one is another liquid. So in order to calculate the Gibbs free energy for the system and as well as spreading coefficient for the two type of system, one parameter is known as interfacial surface tension or interfacial tension, that is between the solid or liquid or between one or the second liquid. The surface tension of any surface can be calculated easily, but the interfacial tension is difficult to calculate. For this purpose, the interfacial tension is derived from the surface tension of the individual components. So here, for example, for a pair of liquids, the surface tension of pure liquids is measured to calculate the interfacial surface tension. So here we have a formula in which interfacial tension is calculated using the surface tension of liquid 1 and the surface tension of liquid 2. And here we also have the same surface tension for the liquid 1 and the liquid 2. And this parameter is known as degree of interaction between two liquids and its value ranges between 0 to 1. And the value of this coefficient is maximum, that is 1 for the strongly interacting liquid. It means that the two liquids exhibit same kind of intermolecular forces, like both liquid can be either polar or both can be either non-polar or non-polar. So for the determination of interfacial tension and spreading coefficient, liquid of high surface tension is kept at the lower substrate. Like in this figure, we also have studied that this substrate can be either solid or liquid, so that this substrate should have higher value of surface tension as compared to the other liquid which is going to get spread or going for the measurement of wetting or spreading coefficient. As I have discussed that the surface interfacial tension, that is surface tension between solid and air, and the interfacial tension between the solid and liquid are difficult to calculate experimentally. So for the two liquid, the interfacial tension can be calculated using this formula, but here another problem is the calculation of solid air tension and as well as the solid liquid interfacial tension. For the determination of liquid solid interface, we have to measure a contact angle. It means we have to place a drop of a liquid on a surface, and so for this purpose select a highly cleaned and polished surface, then put a liquid droplet that should be a finite size, it means that should be visible, and give some time to get settled. So here we can see that the droplet have been casted initially, and after some time the diameter of this droplet is increasing. So this one is the first one, then it's spreading in this manner. So usually the volume of the droplet is taken around 2 microliter, and we can see that the 100 microliter is 1 ml. So this droplet is very small. For this purpose, a micropipette is used. If the liquid exhibit a positive spreading coefficient, it will spread at the surface. Then take some of the shots of the droplet at different times and measure the contact angle. So here we have an example of the two droplets. This one is spreading better as compared to this one. So so here we can see that the greater the angle, lower is the spreading. It means that for this spherical droplet, the angle is higher as compared to the angle made by this liquid drop. So it can also explain that the more flattened droplet exhibits smaller contact angle and thus higher wettability. And here we have examples of 3 droplets. Here L1, liquid 2 and liquid 3. So this one have highest degree of angle. This one has intermediate and the lowest. So the spreading coefficient value will be highest for the liquid 3. As we can see that it's spreading on the surface in a better way as compared to this one. So now for the calculation of solid air and solid liquid interfacial tensions, we measure the contact angle of the liquid. So here we have example. This droplet is occupying a diameter of AB, and from here we can draw the advancing angle, that is theta. So this vector is depicting the value for interfacial tension for liquid air, or that is the surface tension. Here we have surface tension of the solid, whereas this one is depicting the interfacial tension for solid and liquid interface. So for the system, the overall surface tension before and after drop casting is given here using these formula, which give the value of the theta from this relationship. For positive solubility coefficient, that means that the Gibbs free energy of the spreading is negative and spreading is possible. So the solid surface tension must be higher than the liquid's surface tension. Why? Because the solid have the infrastructure of the molecules or atoms which are tightly bounded with each other, so the surface tension must be much higher as compared to the liquid one. For example, the surface tension of the solids ranges between the 700 to 7000 dynes per centimeter, whereas for the liquids it's around about 70 dynes per centimeter, and that is for the organic porous and waxes and other covalent compounds. The surface tension varies between 25 to 100 dynes per centimeter. So it means that all liquids exhibit not more than 75 dynes per centimeter, or around about it. So all liquids can spread over the surface of the solids. Why? Because here we can see that this one is the solid surface tension, and this one is the liquid surface tension. So this parameter is negative, and if this parameter is actually usually lower than the surface tension of the solid, so overall spreading coefficient is positive, leading to the negative Gibbs free energy. And here we can simplify this equation to this equation, and in previous example using drop casting method, the cos theta value was calculated to be this factor, and by so this factor can be replaced with this one. So and then this can be the liquid air interface or the liquid surface tension into cos theta. So here we have the finalized equation, that is the spreading coefficient for the liquid solid interface, that is equal to the surface tension of the liquid into value of the angle. So here we have a finalized form which is free of the two types of interfacial tensions, that is the solid air and the solid liquid. For complete spreading, the spreading coefficient must be positive, or it is 0. It means that the value of the spreading coefficient can be either positive or can be 0. So for the case of 0, here we have maximum or complete spreading here, because here we can see that the angle is 180 degree. So for 180 degree, cos of 180 is -1, but it's more appropriate to call this angle as 0 degree. That is the cos of 0 is 1. If you multiply this factor with 1, so this value is subtracting from the same value, so here we get the spreading coefficient equivalent to 0. So it means that the angle is considered to be 0 degree for complete spreading of the liquid over the solid or solid surface. Now here there are some important points which must be considered. So here first one is in order to make the spreading more positive, it means we can spread the liquid more easily by using a surfactant. When the surfactants are added, they decrease the value of liquid surface tension. So the surfactants lower the liquid air surface tension, and generally by lowering the surface tension of a liquid air or surface of a liquid, we can make the spreading coefficient more positive. So if the surfactant is for example cationic, it will attach to the negatively charged surface, and the non-polar end will be directed to the surface. So here we have a negatively charged surface, and these are the surfactants having a positively charged head. These are the polar heads and the non-polar tail. So here we can see that the positively charged head is directed to the negatively charged surface of the solid. So why these non-polar parts are coming out to the to the air? Because the air is also a non-polar material. Now again consider this diagram. The solid surface has become non-polar due to the adsorption of surfactant at the surface, and the spreading of the polar liquid will not occur. It means that if you have already this diagram, you have a surfactant. This one is the negatively charged surface, and you have poured a surfactant solution. So in this surfactant solutions, you have spreading like this. These are the cationic heads. So here again, after the spreading, you will get the surface like this one. So again, now if you want to pour another liquid over this surface, then the spreading will be prevented, and then the formation of lenses or the droplets, complete spherical droplets, will be observed. Now here we need to consider another information, that is the contact angle hysteresis. Let's understand what is the contact angle hysteresis. It is the advancing angle is always higher than the receding angle. What is the advancing and the receding angle? Here we have two figures, and the angles are usually poured from the micropipette. So if you are advancing the droplet over a solid surface, then the angle is this one, and in other case you are sucking back this liquid to the micropipette. It means you are uh, moving the liquid towards upper direction. So here we have our receding angle. So contact angle hysteresis said that the advancing angle is always higher than the receding angle. Why? It is a universal truth. So even by keeping the surface heterogeneous, the angles also have that much difference, approximately of 60 degree. It means that the advancing angle and the receding angle have a difference of 60 degrees. So when we add a liquid, the liquid is adsorbed at the surface, and when it is sucked back, the liquid is in greater amount with smaller angle. So in some cases it was try to study what is the matter between the that much difference in the two angles. So in the case of steric acids, they showed difference in orientation when gradually released or sucked back. It may be depending on the type of new interaction or the different type of orientation of the polymers or the molecules of the liquid which is getting sucked or released in a form of droplets.